Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Growth or Synthesis of Nanoparticles from the paper Physics at Nanoscale. The learning objectives of this module are: first, we will discuss the nano regime of physics. Second, the different approaches for the achievement of the nanoparticles will be discussed. Thirdly, different types of the deposition and etching techniques will be discussed in this module. Lastly, we will discuss the advantages and disadvantages of physical and chemical deposition techniques. So students, let us start with a basic introduction about the module. Nanomaterials, they are having unique properties arising from their nanoscale dimensions. So, nanomaterials with fast ion transport are related also to nanoionics and nanoelectronics. So, nanoscale materials, they can also be used for bulk applications. Nanomaterials, they are sometimes used in solar cells, which combats the cost of traditional solar silicon cells. So, nanoparticles, which are very important nanomaterials, and their synthesis refers to the methods for creating a nanoparticle. Nanoparticles, they can be derived from either large molecules or synthesized by the bottom-up method, that, for an example, nucleate and grow particles from fine molecular distribution in either liquid or vapor phase. Now there are two techniques to synthesize nanoparticles. First is a bottom-up approach, that is from monolayers to multilayers, and the second one is a top-down approach, that is from multilayers to monolayers. So students, first let us discuss a bottom-up synthesis approach. So under this category, there are four kinds of processes. First is molecular beam epitaxy. Second one is Solgel processing. Third is self-assembly. And the last one is chemical vapor deposition or CVD. So students, let us discuss the first process of bottom-up synthesis approach, that is molecular beam epitaxy. Molecular beam epitaxy, MBE, is an epitaxy method for thin film deposition of single crystals. So as you can see over here, as its name suggests, that it is basically used for growing the epitaxial thin films. Molecular beam epitaxy, it was invented in 1970s, and MBE is an ultra high vacuum, that is UHV based technique for producing high quality epitaxial layers or structures with monolayer control. So now, students, the question arises, what is epitaxial growth? Epitaxy is a kind of interface between a thin film and a substrate. The term epitaxy describes an ordered crystalline growth on a monocrystalline substrate. Epitaxial films may be grown from gaseous or liquid precursors. So because the substrate, as you can see in this figure, act as a seed crystal, the deposited film takes on a lattice structure and orientation identical to those of the substrate. This is different from other thin film deposition methods which deposit polycrystalline or amorphous films even on a single substrate. If a film is deposited on a substrate of the same composition, the process is called homoepitaxy, otherwise it is called as heteroepitaxy. MBE Setup. So as you can see over here, this shows the picture of high mobility applied EPI Gen 2 MBE system installed at TASC INFM National Laboratory in Tricity, Italy. And the figure on the right hand side shows the schematic of a molecular beam epitaxy setup. Now as you can see that the molecular beam epitaxy has several key characteristics which make it an industry and research standard growth system. It is a versatile technique, that is, it is used to make the epitaxial growth films, and here abrupt doping profiles such as delta doping commonly found in high-speed semiconductors can be synthesized. It has slow growth rates which provide for great control over the epitaxial layer thickness, excellent thickness uniformity, minimal foreign contamination as a result of UHV conditions, real-time in situ characterization during growth, high quality multi-wafer growth for high volume production. So as you can see from the schematic that it takes place in an ultra high vacuum chamber, and there are various effusion cells in order to provide the molecular beam, and you can correspondingly study the read pattern, and there are certain vacuum motors to create a high vacuum of the order of 10 to the power minus 10 torr. So this schematic shows the molecular beam epitaxial growth of high quality gallium aluminum arsenide thin films on the gallium arsenide substrate, which is placed below, and there is an ultra high vacuum chamber. Now we can place the effusion cells or the heated cells of each respective element, that is for gallium, aluminum and arsenide, to form the gallium aluminum arsenide thin film in a fixed proportion. So we can make a bulk 3D, a plane 2D, that is quantum well, a line quantum wire 1D, and a nano dot quantum dot 0D. So let us now discuss the characteristics of molecular beam epitaxy. Firstly, it has low growth rate, that is around 1 monolayer, that is one lattice plane per second. It has lower growth temperature, that is around 550 degrees Celsius for gallium arsenide. Thirdly, it has smooth growth surface with the steps of atomic height and large flat terraces. Fourthly, we have a precise control of surface composition and morphology. Next, there is the abrupt variation of chemical composition at the interfaces. Lastly, using this MBE setup, there is in situ control of crystal growth at the atomic level. Why MBE has attracted attention, so much of attention? The reasons are MBE provides the capability to study the crystal growth in real time and on a sub-nanometer scale. The next reason is that we can grow the artificially layered crystals of various thicknesses. That is, we can have a good control over thickness and epitaxial thin films. Now, the below figures shows the TEM images of MBE grown high quality GaN gallium arsenide heterostructures, and the right side figure shows the read pattern of MBE grown heterostructures. Solgel processing. In this chemical procedure, now here as you can see in this figure, the sol gradually evolves towards the formation of a gel-like diphasic system containing both a liquid phase and a solid phase whose morphologies ranges from discrete particles to continuous polymer networks. So in the case of colloid, the volume fraction of particles may be so low that a significant amount of fluid may need to be removed initially for gel-like properties to be recognized. Now, removal of remaining liquid phase requires a drying process which is typically accompanied by a significant amount of shrinkage and densification. So, as you can see in this figure, getting the sol in the gel form, then afterwards we have a thermal treatment or a firing process which is necessary in order to favor the further polycondensation and enhance the mechanical properties and structural stability via final sintering. So, as you can see in this figure, the precursor sol can be either deposited on a substrate by spinning, precipitating and gelling into a wet gel and then coating. The Solgel approach is a cheap and low temperature technique that allows for the fine control of the product's chemical composition. Even small quantities of dopants such as organic dyes and rare earth elements can be introduced in the sol and end up uniformly dispersed in the final product. So as you can see in this figure that we can form using a furnace by spinning the ceramic fibers, the extraction of the solvent from a wet gel and then make it into a dense ceramic, and if we are coating on a zero gel film and gives it a heating treatment, we can get a dense film. Now let us discuss the Solgel processing in detail. That is, we have a sol as shown in this figure, and a sol is a dispersion of the solid particles approximately 0.1 to 1 micron in a liquid where only the Brownian motions suspend the particles. And in the gel form, a sol can become a gel when the solid nanoparticles dispersed in it can join together to form a network of particles that spans the liquid. Principles of molecular self-assembly. So the first figure over here shows the interaction between the molecules, that is, which may be of repulsive interaction and attractive interaction. So the net interaction is shown by the red curve. Now the next is the irreversibility gives the glasses, that is, irreversible association between the molecules. Now reversibility gives crystals as shown in this figure, where as you can see that there is a reversible association between the molecules, and finally we get the ordered macromolecules. Chemical vapor deposition, which is shown clearly in this figure, that is, chemical vapor deposition CVD is used to deposit solid material onto a substrate. So this involves the reaction or decomposition of one or more precursor gases in a chamber containing one or more heated objects to be coated. The reactions occur on and near the hot surfaces where there is a heat source, resulting in the deposition of thin film on the substrate surface. So the chemical byproducts or unreacted gases are then eliminated from the reactor chamber via the exhausting system. So CVD must take place under a vacuum to avoid the inclusion in the film or creation of side products from the reaction of the ambient components with the precursor gases. So let us now discuss the principle of CVD. Chemical vapor deposition CVD is a process whereby a solid material is deposited from a vapor by a chemical reaction occurring on or in the vicinity of a normally heated substrate surface. So a CVD system is constructed in 3 modules, that is, first a reaction gas dispensing system, next is reactor including the components for defining the gas flows, thirdly we have the exhaust system containing a total pressure controller, vacuum pump, scrubber and or the reactant recycle system as shown in this figure. Now there are certain important parameters in the case of CVD. First is the choice of the substrate. Now it is different for the growth of different materials and the important factor for growth kinetics. Second is a substrate temperature, which is important to initiate the associated chemical reactions. Third is the ratio of reacting gases. It is an important factor to control the continuous growth. That is CH4H2, it's a particular example for graphene growth. Third is the growth time. It determines the layered structure, that is, it is monolayer or a multi-layer. Lastly, we have a cooling rate which determined the crystallinity of the film. Examples of CVD grown films. So students, these are the two particular examples of CVD grown films. That is, on the left hand side we have graphene and carbon nanotubes where we have a copper foil, and on annealing in CH4H2 at 1000 degrees Celsius there is a coalescence of graphene domains. On the right side we have TMDs, that is MOS2, WS2 and WES2 monolayers, as which are also evident in this figure, and they are of various thicknesses ranging from 0.5 to 10 nanometers. So let us now discuss the top-down synthesis. Now there are two types of top-down synthesis, that is micro-nano machining, and next is the exfoliation techniques. And again, micro-nano machining are of two types, that is FIB milling and second is electron beam lithography. Next is the exfoliation technique are again of two types, that is a mechanical and a chemical. So students, let us first discuss about the micro-nano machining. Micro-nano machining, M&M, is becoming the cutting edge of high-tech manufacturing because of the increasing industrial demand for super smooth surfaces and functional three-dimensional micro-nano structures in ultra-large scale integrated circuits, micro-electromechanical systems, miniaturized total analysis systems, precision optics, and so on. Micro-nano machining is the basic technology for micro components of sizes in the range of sub-nanometers to few micrometers. And the examples of micro-nano machining are FIB and EBL. Let us now discuss about the focused ion beam. Focused ion beam, also known as FIB, is a technique used particularly in the semiconductor industry, material science, and increasingly in the biological field for site-specific analysis, deposition, and ablation of materials. Now the below figure shows the FIB system which was provided in SEM, and the right hand side figure shows the FIB etching process. In FIB etching process, the primary ion beam, in general the gallium, that is Ga plus ions, hits the sample surface and sputters a small amount of material. So continuing our discussion over FIB system, the left hand side figure shows the various components of FIB system and the right hand side one shows a milling process in FIB. So as evident from this figure, the gallium, that is Ga plus primary ion beam hits the sample surface and sputters a small amount of material which leaves the surface as either secondary ions, I plus or I minus, or neutral atoms N0. So the primary beam also produces secondary electrons E minus. As the primary beam rasters on the sample surface, the signal from the sputtered ions or secondary electrons is collected to form an image. So students, let us now discuss some of the parameters in FIB. Ion beam source, which is having a liquid metal ion sources, especially gallium ion sources. The acceleration voltage of ions, it is typically of the order of 1 to 50 kilo electron volt. So the resolution of the feature size is better than 10 nanometers. So let us now discuss the usage. Micro and nano machining tool to modify or machine materials at the micro and nano scale. So FIB is the commonly used to prepare the samples for the TEM. FIB is also used for secondary ion mass spectrometry, that is SIMS. FIB assisted CVD. Now next is lithography. So students, let us first discuss what is lithography. Lithography is a Greek word. Lithos means stone and graphene means to write. So any technique which can be used for patterning something is known as lithography. So these are the figures which shows some of the examples of lithographic patterns. Electron beam lithography, which paves a route to nano fabrication. Now all these figures indicates the electron beam lithographic patterns. Now students, let us discuss how to proceed to do electron beam lithography. So first we need to have a substrate such as SiO2 over silicon, and then we need to have a resist which can be either positive or negative such as PMMA, then a spin coater. Next we need to have the electron microscopy unit for lithography. Then the next one is to have a metal evaporation chamber. Next is to have a developer solution, that is a mixture of MIBK and IPA. Lastly, the lift-off solution, which we generally take as acetone. Now the question arises, what is a resist? Now resist, basically a photoresist, is of two types, that is a positive resist and a negative resist. Positive resist where the exposed area edged out during developing, and the example of a positive resist is a PMMA. And for a negative resist, the unexposed area is edged out during developing, and the example is SU8. So as you can see in this figure, that for a positive resist, this red portion is edged out, and for a negative resist, the corner portion is edged out rather than the central one. Now students, there are various important parameters in electron beam lithography. First is resist layer thickness, which is typically hundreds of nanometer. Second, the acceleration voltage, 10 to 30 kilovolts. Third is the dose of the incoming beam, which is around 250 to 350 microcoulomb per centimeter square. Lastly, the spot size of the incoming beam, which is around few nanometers. Next is exfoliation technique. The exfoliation technique is useful in the case of materials having layered structures. That is, as shown in this figure, for graphite and for TMDs. So, here we will be discussing the mechanical exfoliation, which is a simple technique and is capable to give monolayers with highest quality. Now, there are various advantages and disadvantages of this technique. Advantages are easy processing, high quality. Disadvantages: poor control, poor reproducibility, small area, low yield, difficult to dope. So students, let us summarize what we have learned in this module. The top-down and bottom-up approach for the synthesis of nanoparticles have been discussed. Secondly, the deposition techniques based on both chemical and physical processes have been explained. Third, the nano-micro machining using different techniques for the fabrication of micro components has been described. Thank you.